Jupiter appears calm from afar, a banded world wrapped in light. Beneath those clouds, Juno finds a planet shaped by deep winds, hidden storms, fierce radiation, and a magnetic engine that stretches millions of kilometers into space. This film follows the descent from the edge of Jupiter's space environment to the quiet clues of its interior, with only measured facts and steady imagery. If this journey feels worth returning to, a like supports the channel, and a subscription keeps future documentaries arriving. One calm discovery at a time, far from Jupiter, where the planet is still only a bright point against a dense field of stars. Space is not empty. It is filled with a thin, fast stream of charged particles that flows outward from the sun. This stream is called the solar wind. It carries mainly protons and electrons, with traces of heavier ions, and it drags with it a magnetic field that is embedded in the flow. At Jupiter's distance, the solar wind is generally cooler and less dense than it is near Earth, yet it still moves at hundreds of kilometers per second, and it still arrives with changing pressure, changing direction, and bursts of turbulence. The quietest stretches feel steady only because the human timescale is short. On longer scales, the solar wind shifts with the sun's rotation, with eruptions from the solar atmosphere, and with the slow breathing of the heliosphere, the bubble carved by the sun into interstellar space. Juno travels through this environment for years before it reaches Jupiter. During the cruise, the spacecraft's instruments learn the background conditions of deep space, the baseline magnetic field in the solar wind, the typical energies of particles, and the character of electromagnetic noise that rides on the flow. This background matters at Jupiter because the planet's influence is sensed as a departure from it. The approach is therefore both a journey and a measurement, with the solar wind acting as the reference medium against which Jupiter's presence becomes clear. As Juno nears the planet, the first signs do not come from clouds or light, they come from fields and particles. The magnetometer records the direction and strength of the magnetic field around the spacecraft. In the undisturbed solar wind, that field tends to follow a spiral pattern shaped by the rotating sun, and it flickers with waves and sudden turns. The particle sensors, including instruments designed to count low-energy ions and electrons and others designed for higher-energy particles, measure how many particles arrive from each direction and how their energies change. The radio and plasma wave instrument listens to electric and magnetic fluctuations, revealing where plasma becomes more disturbed. Together, these measurements track the solar wind as it begins to feel a large obstacle ahead. Jupiter's magnetic field is enormous. Even before the spacecraft reaches the planet's immediate neighborhood, the solar wind has to flow around a magnetic bubble. That bubble is called a magnetosphere, meaning a region where a planet's magnetic field dominates the motion of charged particles. For Jupiter, the magnetosphere is so large that it can extend millions of kilometers toward the Sun and still remain many times larger than the planet itself. Its size is not fixed. It expands when the solar wind pressure drops, and it compresses when the solar wind grows stronger. A fast solar wind stream can squeeze the boundary inward. A solar eruption can press harder and trigger a sudden reconfiguration. These changes leave signatures that Juno can detect while it is still outside the magnetic bubble. The solar wind does not simply slide smoothly around Jupiter. When a supersonic flow meets a strong obstacle, it typically forms a shock, a thin region where the flow slows, heats, and becomes more turbulent. Around Jupiter, this bow shock stands upstream of the magnetosphere, shaped like a curved surface facing the Sun. In front of it, the solar wind can be relatively calm. Behind it, the solar wind becomes shocked plasma, with stronger waves and a broader spread of particle energies. Juno's approach is often marked by a gradual increase in magnetic fluctuations and by changes in the distribution of particles, as if the solar wind is growing restless. The transition across the shock can be sharp. The magnetic field may jump in strength. Particles may suddenly appear more heated, with a wider range of velocities. Plasma waves can intensify, producing a richer spectrum of noise. In this outermost region, certainty comes from repeated patterns rather than from direct sight. The spacecraft's data show that Jupiter's outer boundary responds to the solar wind in a dynamic way. Observations indicate that the shock and the magnetic bubble move inward and outward on timescales of hours to days, and that the location of the boundary depends strongly on the pressure of the incoming flow. It remains uncertain how much of the observed variability is driven by the solar wind alone, and how much is influenced by processes inside Jupiter's magnetic environment, since internal plasma sources and rotation can also reshape the system. Even so, the solar wind sets the stage by providing the external force that presses on the boundary and by carrying the embedded magnetic field that can connect, in certain configurations, to planetary field lines. Juno's measurements allow the solar wind at Jupiter to be studied in its own right. At that distance, the solar wind has evolved from its state near the Sun. Streams of fast and slow wind have interacted and merged, forming broad regions of compressed plasma called interaction regions. These regions can produce repeated patterns in particle density and magnetic field strength as they sweep past. Juno detects such structures during the approach and during later orbits, when it briefly returns to the solar wind between passes through Jupiter's space environment. When an interaction region arrives, the solar wind becomes denser, and the magnetic field grows stronger for a time. Energetic particle populations can increase, not because Jupiter is directly producing them at that moment, but because the solar wind itself carries shocks and compressions that accelerate particles. The far upstream region also highlights the scale of Jupiter's influence. The planet sits inside the heliosphere like a massive boulder in a river, but a boulder that carries its own magnetic strength and its own internal energy. The solar wind is forced to divert, and the diversion begins long before any atmospheric feature can be resolved. In the data, this influence is seen as a gradual shift from the relatively uniform solar wind to a regime where waves become more intense, and where the magnetic field begins to show the imprint of a large, organized system ahead. The approach is therefore an exercise in patience. Each instrument reads a different aspect of the same thin medium, and together they reveal that the space around Jupiter is layered, not by visible surfaces, but by the changing balance between a wind from the Sun and a magnetic domain anchored deep within a giant planet. Jupiter's magnetic domain begins where the direct push of the solar wind can no longer force its way inward. The boundary that marks this change is called the magnetopause, a surface defined by balance between the pressure of the solar wind and the pressure of Jupiter's magnetic field and trapped plasma. Outside that surface, the solar wind has been slowed and heated by the bow shock, and now flows in a disturbed layer called the magnetosheath. Inside the surface, charged particles largely follow Jupiter's magnetic field, and the planet's rapid rotation starts to dominate the motion of matter and energy. Juno crosses this boundary many times across the mission, and each crossing differs because the boundary shifts with changing conditions. The outer magnetosphere is not a hard shell. It is a region where the solar wind presses, slides, and sometimes connects to Jupiter's field. The magnetometer senses the change as a shift from the solar wind field, which is carried past the spacecraft, to a stronger and more ordered field that is anchored to the planet. At the same time, the particle instruments register a change in direction and in energy. In the magnetosheath, particles arrive as a flowing stream with strong turbulence, and the range of energies is broadened by the shock. Inside the magnetopores, particles more often show motion that is guided by magnetic field lines, with patterns that reflect both the external push and internal circulation. The radio and plasma wave instrument also hears a different environment, with wave activity that reveals density changes and boundaries that remain invisible to cameras. In this region, a central term is plasma, meaning gas in which a significant fraction of atoms are split into charged particles. Plasma responds to electric and magnetic fields, and it can carry currents that in turn reshape the fields that guide it. Jupiter's outer magnetosphere contains plasma that is stirred by both the solar wind and the planet's rotation. Observations indicate that the solar wind supplies some particles directly and also controls how easily energy enters the system. While it remains uncertain how the balance between solar wind driving and rotation-driven circulation changes from one set of conditions to another. Jupiter rotates in about 10 hours, and its magnetic field rotates with it. That rotation acts like a giant electric generator. Even in the outer magnetosphere, far from the cloud tops, the field tries to pull plasma into co-rotation, the tendency for plasma to circle the planet along with the magnetic field. Co-rotation is not perfect at large distances because plasma has inertia and because the solar wind presses on the outer boundary. The result is a gradual lag that grows with distance. Juno detects this through the direction of particle flows and through the way the magnetic field bends and stretches. When plasma lags behind rotation, electric fields develop that help drive currents, and those currents produce distortions in the magnetic field that the magnetometer can measure. The shape of the outer magnetosphere is controlled by the flow of the solar wind and by Jupiter's own rotation. On the day side, the magnetopause is pushed inward and forms a rounded obstacle. On the night side, the magnetic field is drawn into a long tail, where field lines are stretched away from the sun. This tail is a common feature of magnetospheres, but at Jupiter it is influenced strongly by rotation and by the presence of large amounts of plasma. In the outer regions, the tail can be wide and complex, with boundaries that move and ripple. Juno's trajectory, which often passes over the poles and dives close to the planet, allows it to sample the outer magnetosphere at different latitudes, including regions where field lines connect more directly to the solar wind. Energy enters the outer magnetosphere through several pathways. One pathway involves reconnection, a process in which magnetic field lines from different regions break and join in a new pattern, converting magnetic energy into particle motion and heat. When the magnetic field carried by the solar wind is oriented in a way that can link to Jupiter's field, reconnection can occur near the dayside boundary. The result is a transfer of energy and plasma across the magnetopores. Another pathway involves waves and instabilities along the boundary. As the magnetosheath flow slides past the magnetopores, it can create rolling motions that mix plasma from outside and inside. These motions can transport particles and momentum and can stir the boundary into a layered, fluctuating structure. Juno's measurements show that Jupiter's outer magnetosphere does not behave as a simple copy of Earth's. The enormous size, the rapid rotation, and the strength of the internal magnetic field create a system where internal circulation can remain strong even when the solar wind is quiet. The outer regions can store energy in stretched field lines and in hot particle populations, then release it through gradual rearrangements or more abrupt changes. Observations indicate that some disturbances resemble substorms at Earth, with changes in the tail and injections of energetic particles toward the planet. while it remains uncertain how closely these events match terrestrial processes, given the stronger role of rotation. The outer magnetosphere is also a place where currents form large-scale patterns. Currents can flow along magnetic field lines into and out of the polar regions, and they can also flow across the magnetosphere in broad sheets. These currents are not directly visible, but they leave magnetic signatures that Juno can detect as small deviations from an ideal dipole field. In the outer regions, such deviations can indicate the presence of a current sheet in the tail, where field lines from the northern and southern hemispheres lie close together with opposite directions. The plasma there can be hotter and more variable, reflecting the tension between the outward stretch of rotation and the inward pull of magnetic forces. Across this region, the boundary between order and turbulence shifts constantly. The solar wind continues to apply pressure and to deliver changing conditions. Yet Jupiter's rotation continues to impose a steady rhythm. Juno's repeated crossings allow the outer magnetosphere to be seen not as a static shell, but as a broad interface, where solar plasma meets a rotating magnetic world, and where particles, fields, and waves interact in slow, continuous ways that instruments can trace with precision. Within Jupiter's magnetic domain, there is a region where the motion of charged particles becomes not only guided but confined. This is the domain of the radiation belts, broad zones where energetic electrons and ions are trapped by the planet's magnetic field and can persist for long periods. In these belts, the space around the planet is filled with fast particles that carry enough energy to damage electronics and alter exposed materials. Juno passes through this environment with instruments designed to measure particles and fields, while the spacecraft itself is protected by shielding and by careful planning of how long it remains in the most intense zones. Trapping begins with the way a charged particle moves in a magnetic field. The particle spirals around an invisible line of magnetic force while also sliding along it. As the particle travels, it encounters regions where the magnetic field is stronger closer to the planet. Under many conditions, that increase acts like a mirror. The spiral tightens, and the particle is turned back before it can reach the dense atmosphere. The result is a repeated bounce between the northern and southern hemispheres. While bouncing, the particle also drifts sideways around Jupiter. This drift comes from the slow change of field strength with position and from large-scale electric fields. Over time, the particle can circle the planet, forming a ring-like population. The term radiation belt describes a population, but it also implies a set of processes that maintain it. Particles must be supplied, moved into trapping regions, accelerated, and eventually removed. Observations indicate that Jupiter's strongest belts contain electrons with energies of millions of electron volts, along with ions that can also reach very high energies. The intensity is among the most severe in the solar system. It remains uncertain how much of the highest energy population is built mainly by gradual inward transport compared with more local acceleration, because several mechanisms can operate together. Juno separates these mechanisms by measuring multiple parts of the environment at once. Jade measures lower energy ions and electrons, tracing the background plasma that provides the raw material for higher energy populations. Jedi measures more energetic particles, revealing how their intensities and directions change along the spacecraft path. The magnetometer records the precise field that guides the particles, and the radio and plasma wave instrument detects electromagnetic waves that pass through the plasma and sometimes exchange energy with particles. These combined measurements show that the radiation belts are not smooth shells. They have peaks and gaps, and they differ between electrons and ions because each responds differently to fields, waves, and loss processes. One reason the belts become so intense is the strength of Jupiter's magnetic field. A strong field confines particles more tightly and allows them to store more energy before they are scattered away. Another reason is rotation. Jupiter spins rapidly, and that rotation drives electric fields that tend to pull plasma into circulation with the planet. The motion is not perfect at all distances, yet the attempt to co-rotate sets up currents and electric potentials that can move particles inward. When a trapped particle is transported inward towards stronger magnetic fields, its energy can rise through a gentle form of compression. The spiral motion speeds up in the stronger field, and the particle can gain energy without a single violent collision. In this way, slow changes in position can translate into large changes in energy. Acceleration also occurs through interactions with waves. In the radiation belts, electromagnetic waves propagate through plasma and can resonate with particles whose motion matches the wave pattern. In resonance, energy and momentum can be exchanged. Some interactions increase particle energy, while others mainly scatter the direction of motion. A useful measure here is pitch angle, the balance between motion along the magnetic field line and motion around it. When scattering shifts a particle into a direction that points more strongly along the field line, the particle can travel deeper toward the atmosphere. There, collisions with neutral gas remove it from the belt. This pathway shapes sharp edges and persistent holes in the trapped population. Juno observes evidence for these interactions in the way particle distributions change across space. There are regions where fluxes drop rapidly, consistent with strong scattering and loss. There are also regions where particle intensities vary more gradually, consistent with diffusion, a slow wandering in energy and position driven by many small interactions. The wave instrument detects bands of activity that rise and fall with location, and the particle instruments show changes that are consistent with waves altering pitch angles and energies. Observations indicate that the belts respond to broad disturbances in Jupiter's magnetic environment, including compressions and expansions that change the field strength and the electric fields that guide transport. It remains uncertain which wave types dominate the energization of the most extreme electrons, because the environment supports more than one wave mode, and because each spacecraft samples only a narrow slice of a vast system. Loss processes are as important as acceleration. A trapped particle can be removed when scattering pushes it into atmospheric loss paths, and it can also be removed when gradual transport carries it outward to weaker trapping regions where escape becomes easier. Collisions are rare in the thin plasma of space, yet interactions with waves and fields provide effective ways to change trajectories. Over time, these losses compete with supply and acceleration, setting the steady intensity of the belts. Juno's repeated passages show that some structures are stable, tied to the enduring shape of Jupiter's internal field, while other features vary, reflecting changes in wave activity and in the electric fields that move particles inward and outward. In the radiation belts, Jupiter is revealed as a system that stores energy in trapped particles and releases it through slow scattering, gradual diffusion, and occasional reorganizations of fields and waves. Energetic electrons in the belts also produce radio and microwave emission that can be detected from far away. Juno's instruments record how a magnetic field can sculpt motion into confinement, and how confinement, maintained over time, turns charged particles into a persistent ring of radiation around a giant world. The outer space around Jupiter is shaped not only by the solar wind and the planet's own field, but also by a steady supply of fresh material that comes from within the system. This supply is not primarily from Jupiter itself as neutral gas escaping from the cloud tops, but from the environment of its inner moons and the dust that moves among them. The magnetosphere is therefore fed by sources that are small in size compared with the planet, yet large in consequence because they provide ions and electrons that become the working substance of the magnetic domain. Juno's instruments sense this supply as patterns in plasma composition, density, and flow that cannot be explained by the solar wind alone. A key idea is that plasma in Jupiter's magnetosphere is not a closed population. Neutral atoms and molecules can be released from moons, rings, and dust grains, then become ionized by sunlight or by collisions with energetic particles. Once ionized, they are captured by Jupiter's magnetic field and begin to move with it. This capture process turns a local release of material into a magnetospheric reservoir that can spread across vast distances. The material becomes part of the circulating plasma that drifts, co-rotates, and participates in currents and waves. Among the sources, Io is the most dominant. It is a moon with intense volcanic activity, driven by tidal forces that flex its interior. Volcanic plumes release large amounts of sulfur and oxygen compounds into space. Around Io's orbit, these gases form a cloud of neutral material. When ionized, they create a dense torus of plasma, a donut-shaped ring of charged particles that encircles Jupiter along Io's orbital path. Even far from this torus, its influence extends outward because plasma can be transported by electric fields and can spread along magnetic field lines. Observations indicate that this source is a major contributor to the mass loading of Jupiter's magnetosphere, meaning the process of adding mass that must then be carried by the rotating field. It remains uncertain how the supply rate changes over time with Io's volcanic activity and with variations in the magnetospheric environment, because both the source and the ionization conditions can vary. Other moons contribute in different ways. Europa, Ganymede, and Callisto possess surfaces of ice and rock, and they interact with Jupiter's magnetic environment by releasing particles and by acting as obstacles in the plasma flow. Sputtering, the process in which energetic particles strike a surface and knock atoms or molecules free, can release oxygen and water-related fragments from icy surfaces. These neutrals can then be ionized and incorporated into the magnetosphere. In addition, the moons can create local disturbances in the plasma because they absorb particles and because their atmospheres, even if thin, can slow and alter the flow nearby. Ganymede is especially notable because it has its own magnetic field, creating a small magnetosphere embedded inside Jupiter's larger one. While Juno's high-latitude passes are not designed to linger near these moons, the global signatures of their interactions can still be inferred through changes in plasma populations and through the distribution of energetic particles. Dust also plays a role. Jupiter has faint rings made largely of small particles that are continually replenished by impacts on small inner moons. Dust grains can become electrically charged by sunlight and by interactions with plasma. Once charged, they can be influenced by magnetic and electric fields and can follow complex paths. Some dust escapes and some spirals inward or outward depending on its size and charge. In addition to rings, dust can be produced by micrometeoroid impacts on moons, releasing tiny grains and neutral material that can feed into the plasma environment. Juno's instruments that measure fields and plasma waves can detect signatures of dust indirectly, because dust affects plasma density and can modify the way waves propagate. The particle instruments can also sense changes in the composition and energy of ions that reflect different source materials. The supply of plasma has consequences for the entire magnetosphere. Added mass makes it harder for the magnetic field to enforce co-rotation at large distances. As plasma is loaded into the system, the rotating field must transfer momentum to it. This transfer is achieved through electric fields and currents, which couple the outer magnetosphere to Jupiter's upper atmosphere. In simple terms, the magnetosphere tugs on the ionized upper atmosphere and the atmosphere tugs back, allowing angular momentum to be exchanged. The result is a large-scale circulation where plasma tends to drift outward while conserving angular momentum, and where currents flow to maintain near co-rotation. This outward transport is slow but persistent, carrying material from the inner source regions toward the outer magnetosphere and tail. Juno's measurements reveal that the composition of plasma changes with location, consistent with multiple sources. In regions influenced by Io, ions containing sulfur and oxygen are common. Farther away, the mixture becomes more altered by transport, by charge exchange with neutral atoms, and by interactions with the solar wind near the boundary. Charge exchange is a process in which a charged ion steals an electron from a neutral atom, becoming neutral itself while the former neutral becomes an ion. This can remove energetic ions from the trapped population and create fast neutrals that travel in straight paths, no longer guided by magnetic fields. Over time, such exchanges help shape the distribution of ions and can create pathways for energy and mass to leave the system. The moons and dust therefore act as quiet contributors to Jupiter's space environment. They provide material that becomes plasma, plasma that becomes currents, and currents that become auroral power at the poles, even in the outer regions where the solar wind presses on the boundary. The internal supply continues to influence the system by providing the bulk of the mass that circulates within. Juno's data show a magnetosphere that is not merely a shield against the solar wind, but a rotating, living domain fed from within by small bodies that orbit in the planet's shadow and light. Near Jupiter's poles, the boundary between space and atmosphere becomes thin in a different way than it does at lower latitudes. Magnetic field lines that rise from the planet's interior extend outward into the magnetosphere and guide charged particles toward the upper air. Where those particles arrive, light appears. The glow is called an aurora, meaning a luminous response of the atmosphere to energetic particles and electrical currents. At Jupiter, auroras form persistent ovals around each pole, along with arcs and spots that shift with changing plasma flow above. Juno samples these regions on close polar passes, moving from the magnetosphere down toward the top of the atmosphere while measuring particles, fields, and faint emissions. Auroral light is produced high above the visible clouds, in rarefied layers where gas is thin enough that collisions are limited, yet frequent enough that excited atoms and molecules can shine. When fast electrons plunge downward, they strike hydrogen and trace gases, transferring energy that pushes atomic and molecular electrons into higher states. As those states relax, ultraviolet and infrared light is emitted. Juno observes part of this glow with an ultraviolet spectrograph and with an infrared mapper. The ultraviolet view traces energetic impacts and the distribution of hydrogen emission, while the infrared view is sensitive to a charged hydrogen molecule that forms in ionized regions and radiates strongly. Its brightness responds to temperature and density, allowing the upper atmosphere's warmth to be mapped. Auroras are not only light, they are the visible endpoint of electrical circuits that connect the magnetosphere to the planet. In the polar regions, electric currents flow along magnetic field lines. These are called field-aligned currents, meaning currents that run parallel to the magnetic field. They are carried by streams of charged particles. When these currents reach the upper atmosphere, they close through the ionosphere, a layer where sunlight and particle impacts create enough charged particles for the air to conduct electricity. This closure completes a circuit that allows momentum and energy to be exchanged between the rotating magnetosphere and the upper atmosphere. Jupiter's auroras are shaped by the planet's rapid rotation and by the heavy plasma that circulates in the magnetosphere. As plasma loaded from the moons moves outward, the magnetic field works to keep it near co-rotation. Where co-rotation lags, electric fields and currents develop that link to the polar regions. Those currents can accelerate electrons downward, giving them the energy needed to create auroral emissions. Observations indicate that this rotation-driven system powers much of Jupiter's main auroral ovals, even when the solar wind is quiet. It remains uncertain how the detailed acceleration varies from place to place, because more than one mechanism can operate, including electric potential drops along field lines and interactions between particles and waves. The shape of the auroras reflects the geometry of Jupiter's magnetic field. The main ovals mark boundaries between regions where magnetic field lines are mostly closed, looping back to the planet, and regions where they connect outward into the distant magnetosphere. Small shifts in that mapping move the oval. When the solar wind pressure rises, the magnetosphere compresses and the mapping of field lines to the polar atmosphere can change. Juno detects these changes as variations in the magnetic field and as shifts in particle populations, and the ultraviolet and infrared emissions adjust in response. The auroras therefore respond to both internal circulation and external forcing, with the balance changing over time. Jupiter's auroras are not symmetric rings. Brightness often differs between the dawn and dusk sides, and smaller structures appear inside the ovals in the polar cap, a region threaded by field lines that reach far into the magnetosphere. Juno's close polar geometry allows these differences to be compared with simultaneous measurements of incoming particles. In some cases, narrow features align with magnetic connections to inner moons, where a moving obstacle in the plasma can drive currents that map to the atmosphere as compact bright spots. The upper atmosphere that hosts the auroras is often called the thermosphere, a region where temperature rises with height because energy is deposited from above. At Jupiter, the thermosphere is hotter than sunlight alone would suggest. Auroral energy is one cause. Particles deposit energy directly where they collide, and currents deposit energy through Joule heating, the warming that occurs when electrical currents pass through a conducting medium with resistance. Infrared observations show that heating is not confined to a thin ring. Warmth can spread through winds and waves, carrying energy away from the brightest zones and altering the broader polar region. Juno's measurements also show that the polar regions are sites of complex electromagnetic activity. The plasma wave instrument detects strong radio emissions associated with auroral processes, produced when energetic electrons interact with magnetic fields and generate coherent radiation. In the local environment, waves can also influence particle motion, scattering electrons into the atmosphere or accelerating them along field lines. The particle instruments record beams and bursts that indicate active acceleration regions above the atmosphere, and the magnetometer detects subtle perturbations that mark the presence of currents and changing field configurations. Together, these data reveal auroras as dynamic systems rather than fixed decorations. The light itself carries information about energy and altitude. Ultraviolet spectra reveal how deeply particles penetrate. Because different emissions favor different pressure levels, infrared emissions respond to temperature and the abundance of ionized molecules, providing a view of how heating varies across the polar cap and along the oval. Observations indicate that some regions brighten in bursts, consistent with intermittent injections of energy from the magnetosphere. It remains uncertain how far downward the influence of these bursts extends, because the upper atmosphere transitions gradually into denser layers where emissions change and direct diagnosis becomes less straightforward. In this polar region, Jupiter appears as a planet whose atmosphere and space environment are tightly coupled. Magnetic field lines guide particles down. The atmosphere conducts and completes currents, and the resulting energy input drives heat and motion high above the clouds. Juno's passes across the poles trace this coupling in steady detail, showing how a giant planet's upper air responds to invisible currents with enduring light and with warmth that lingers in the thin, high layers of Jupiter's sky. Between the bright auroral heights and the familiar cloud tops lies a quieter layer that still carries the marks of sunlight and chemistry. This region is Jupiter's stratosphere, a zone above the main weather where temperature tends to rise with height because gases and haze absorb energy and re-radiate it. Compared with the churning clouds below, this stratosphere changes more slowly. Winds still move there, and waves still pass through, but the motions are gentler and the structures are often thin and widespread, like veils spread across a rotating globe. In visible light, the first sign of this region is haze. A haze is made of tiny particles suspended in gas, too small to be called clouds of droplets or ice in the usual sense, yet large enough to scatter and absorb light. Jupiter's high hazes soften the sharp edges of belts and zones, tint the planet's limb where sunlight travels through a long path, and add faint colour gradients that shift with latitude and season. The particles are not uniform. Some are likely made of condensed compounds that rise from below, while others are formed higher up by chemical reactions driven by sunlight. The raw material for much of Jupiter's stratospheric chemistry is methane, a simple molecule that is abundant in the upper atmosphere. When ultraviolet sunlight reaches methane, it can break it apart, starting a chain of reactions. This process is called photochemistry, meaning chemistry initiated by light. The fragments recombine into heavier hydrocarbons, molecules made of hydrogen and carbon. Among the common products are ethane and acetylene, which build up in the stratosphere and act as traces of circulation and mixing. The same reactions can lead, through many steps, to larger molecules that can clump into aerosols, meaning solid or liquid particles suspended in gas. Over time, these aerosols contribute to the haze layers that Juno and other observers detect. Juno studies this region from a moving vantage point that often looks down along steep angles. Its infrared mapper senses heat and certain molecular emissions, allowing temperature patterns in the upper atmosphere to be inferred. The ultraviolet instrument adds information about how sunlight is absorbed and re-emitted, especially in polar regions and at high altitudes. The visible camera records subtle brightness variations and color tones, which are shaped by how haze scatters sunlight. Together, these measurements show the stratosphere as a layer that is not uniform but patterned by belts, waves, and changing concentrations of gases and particles. One persistent pattern is a contrast between regions that look clearer and regions that look more muted. Where haze is thicker, the planet's features appear softer, and the colours can shift toward paler tones. Where haze is thinner, deeper cloud structures show through more sharply. The distribution of haze is affected by vertical motion. Upward motion can loft particles and gases, increasing haze abundance at high altitudes, while downward motion can dry and clear the air. Because Jupiter rotates rapidly, its atmosphere forms jet streams, and these jets can organize the stratosphere as well as the weather below, shaping where material accumulates and where it is carried away. Temperature in the stratosphere is not fixed. It varies with latitude and with local heating. Sunlight is the primary driver in most regions, yet the planet's internal heat still matters indirectly because it shapes the circulation that moves gases upward and downward. At high latitudes, Auroral processes deposit energy from above, warming the upper atmosphere and influencing the layers beneath. This heating can produce temperature contrasts that drive winds around the poles. Infrared maps show that polar regions can differ strongly from equatorial regions, with warm and cool patches that shift over time. Observations indicate that waves and vortices contribute to these patterns, while it remains uncertain how deeply some of the polar stratospheric structures extend. Since measurements sample emission layers that represent broad altitude ranges rather than sharp surfaces, the chemistry of the stratosphere also responds to mixing. If gases are stirred upward from deeper layers, they carry different compositions into sunlight, changing the balance of reactions. If the stratosphere is isolated and mixing is weak, photochemical products can accumulate and form thicker hazes. A useful term here is eddy mixing, meaning the slow transport of gases by turbulent motions and waves that blend layers together. Eddy mixing is hard to measure directly at Jupiter, but it leaves fingerprints in how the abundance of hydrocarbons changes with height and latitude. Juno's infrared observations, combined with other data, indicate that mixing varies across the planet, helping explain why some regions show richer hydrocarbon signatures than others. Color in Jupiter's upper atmosphere remains an area where observations guide but do not close every question. The reddish and brownish tones of some belts and features suggest the presence of chromophores, compounds that absorb certain wavelengths of light and therefore color the reflected sunlight. Several candidates exist, including complex organic molecules and sulfur-bearing compounds, produced by reactions among gases and energetic particles. Haze particles can carry these coloring agents, spreading them thinly across wide regions or concentrating them where circulation gathers material. Observations indicate that changes in haze thickness can alter color contrasts without requiring a complete change in deep clouds. It remains uncertain which specific molecules dominate the coloring in each region, because multiple compounds can produce similar broad effects and because the particles are small and mixed. The stratosphere also preserves memory of events that disturb the upper layers. When high-energy particles rain down in auroral regions, they can alter chemistry by breaking molecules apart and creating reactive fragments. When a comet or asteroid enters the atmosphere, it can inject dust and unfamiliar compounds high above the clouds, leaving dark or hazy marks that slowly spread and fade. Over time, sunlight and circulation smooth these disturbances, yet the stratosphere's slow pace means that some signatures can persist longer than the storms below, offering a record written in faint veils and shifted spectra. In this region, the planet feels more like a laboratory of thin gases than a landscape of towering clouds. Sunlight arrives, breaks molecules, and sets in motion chains of reactions that build new compounds. Winds carry the products around the globe, and vertical motions decide whether the haze grows thicker or thins away. Juno's instruments translate these quiet processes into maps of temperature, brightness, and composition. The result is a view of Jupiter's upper layers as a place where light, chemistry, and slow circulation meet, forming hazes that drift above the main cloud decks. Below the hazes of the stratosphere, Jupiter's familiar face appears. The planet's visible surface is not a solid boundary, but a level in the atmosphere where clouds become thick enough to reflect sunlight strongly. From a distance, the most striking feature is a pattern of bands that wrap around the globe. These are the belts and zones, long ribbons of differing colour and brightness that mark differences in cloud height, chemistry, and motion. Belts tend to look darker and more brown, while zones tend to look brighter and more pale. The contrast is not only a matter of colour, it reflects where air rises and where it sinks, where clouds thicken and where they thin, and where sunlight penetrates deeper before scattering back to space. Juno approaches these cloud tops from a polar orbit, seeing the banded planet at changing angles as Jupiter turns beneath. The camera records the visible patterns in fine detail, capturing the texture of cloud layers and the small storms embedded within the bands. In this region, the atmosphere is dense enough that clouds form and persist, yet transparent enough above the main decks that light still reveals structure from above. The belts and zones are organized by Jupiter's rapid rotation. Fast spin encourages flows to align in east to west directions, and the result is a set of jet streams, fast winds that circle the planet in alternating directions. A jet stream is a narrow band of faster wind that forms where neighboring air masses slide past one another. At Jupiter, these jets mark many of the boundaries between belts and zones. Where a jet moves eastward, it often lies next to another that moves westward, and the shear between them stretches storms into long ovals and filaments. Juno's images show that boundary regions can be intricate, filled with swirling eddies and chains of small vortices that appear, merge, and fade. Brightness differences across the bands come from the height and thickness of clouds. When air rises, it cools, and certain gases can condense into cloud particles. Ammonia is an important condensable gas in Jupiter's upper atmosphere, and ammonia ice can form bright clouds that reflect sunlight efficiently. In many zones, rising motion is more common, leading to higher and thicker cloud layers that look pale. In many belts, sinking motion is more common, warming and drying the upper levels and thinning the bright clouds, allowing darker material from deeper levels to influence the colour. This picture remains a guide rather than a fixed rule, because local storms can overturn the usual pattern for a time. The cloud tops are not smooth layers. They are shaped by convection, the vertical movement that occurs when warmer, lighter gas rises and cooler, heavier gas sinks. Convection at Jupiter draws energy from the planet's internal heat as well as from sunlight. Internal heat is a quiet but persistent driver, rising from below and supporting powerful storms in particular regions. The visible cloud tops show this in bright plumes that rise and spread, and in darker gaps that open where air sinks. These features are often organized by the jet streams, which guide plumes into lanes and confine them between faster winds. Color variations add another layer of meaning. Jupiter's upper clouds are dominated by pale whites and creams, yet many belts carry ochre and reddish tones. These colors are influenced by cloud thickness, by haze particles mixed into the upper clouds, and by compounds that absorb blue and ultraviolet light. The exact identity of the coloring agents remains uncertain. Observations indicate that some colors deepen when cloud decks thin, suggesting that darker material from below, or particles altered by chemistry and radiation, become more visible. It remains uncertain which specific compounds dominate at every latitude, because several candidates can produce similar broad effects and because the atmosphere continually mixes and transforms the particles that carry color. Jupiter's cloud tops also host vortices, long-lived storm systems that rotate around calmer centers. A vortex forms when winds circle a region, trapping material inside and often creating a distinct oval. The Great Red Spot is the best-known example, a vast storm in the southern hemisphere that persists for centuries in telescopic records. Juno sees it as a complex field of motion, with rings and filaments around the perimeter, and a calmer interior that still contains smaller swirls. Its boundary can tighten or loosen as surrounding winds shift. Around it, smaller ovals drift along the jets, some bright and some dark, many with sharp edges where fast winds wrap around them. When vortices meet, they can merge or pass by with limited interaction, depending on their size, spin, and the jets that steer them. The belts and zones are not fixed stripes painted on a globe. They are dynamic lanes of flow that evolve on many timescales. Over months and years, belts can fade and then darken again, and zones can brighten or become disrupted by outbreaks of storms. These changes reflect shifts in vertical circulation and cloud formation, with bright clouds spreading over darker regions and later retreating as sinking motion clears the upper layers. Juno's close-range views reveal how such changes are built from countless small motions, filamentary clouds stretched by shear, eddies that mix neighbouring air, and plumes that rise, spread, and dissolve. Waves also pass through the cloud tops. In the visible layer, waves appear as rippling patterns and evenly spaced bands embedded in the clouds. They arise when winds flow through layers that resist mixing, allowing disturbances to travel as organized motion rather than breaking apart immediately. Some waves align with jet streams and trace boundaries where winds change rapidly, while others ride across broader regions, marking stability in subtle texture. In this visible region, Jupiter's upper atmosphere becomes a moving skin shaped by rotation, heat, and chemistry. The belts and zones trace the balance between rising and sinking, between thick, bright clouds and thinner windows into deeper layers, and between steady jets and the turbulence that grows along their edges. Juno's observations make the cloud tops feel less like a surface and more like a living system of flow, where sunlight falls on drifting vapor and ice, and where large-scale order is renewed by persistent motion. Beneath the bright cloud tops, Jupiter's atmosphere continues without a clear boundary. Reflected sunlight cannot reveal what lies below for long, because deeper layers become opaque to visible wavelengths. Juno reaches into this hidden region with an instrument that does not depend on light. The microwave radiometer measures the planet's own thermal glow at several microwave wavelengths. Microwave energy passes through thin hazes and many cloud particles more readily than visible light, yet it is absorbed by certain gases, especially ammonia, and deeper down, water and other constituents. Each wavelength therefore samples a different range of pressures. Shorter microwave wavelengths tend to emerge from higher, cooler layers. Longer wavelengths can escape from deeper, warmer layers. The radiometer uses 6 channels, spaced so that each one looks through the atmosphere with a different degree of penetration. Together they sense conditions from near the upper cloud decks down to regions where pressure reaches many tens of bars, and in the deepest channel, potentially to pressures of a few hundred bars. These pressures correspond to depths of thousands of kilometers beneath the visible clouds, where sunlight plays little direct role. Even there, the gas remains an atmosphere, not a surface, and it continues to move and mix. The radiometer records brightness, the amount of microwave energy arriving at the spacecraft from each direction. That brightness can be expressed as a brightness temperature, a practical way to compare the signal to emission from a warm body. There is no solid surface to radiate from Jupiter. Instead, the signal comes from depths where the atmosphere becomes transparent enough at that wavelength for radiation to escape. When ammonia is abundant, it blocks microwaves more strongly and shifts the effective emitting layer upward to cooler air. When ammonia is depleted, the radiometer can see deeper into warmer air. Temperature and composition are therefore coupled, and Juno uses its multiple channels to reduce the ambiguity by comparing patterns across wavelengths. As the spacecraft passes over belts and zones, the microwave map shows that Jupiter's banded organization extends downward, while the distribution of ammonia does not reduce to a simple, uniform background beneath the clouds. Observations indicate that ammonia is enriched near the equator, in a broad band that persists across channels that probe to substantial depths. The persistence implies that the enrichment is not confined to a thin layer near the cloud tops. The pattern is consistent with sustained upward transport in the equatorial atmosphere, bringing ammonia-rich air from deeper levels toward higher regions before it spreads and mixes. The equatorial band becomes a slow marker of deep circulation rather than a surface stain. Away from the equator, the picture changes. In many mid-latitude regions, ammonia appears depleted to depths greater than expected from a well-mixed atmosphere below the condensation level. Instead of settling toward a nearly uniform abundance, the tracer remains structured with latitude down to pressures of many bars. This implies that Jupiter's circulation reaches far beneath the visible clouds. Broad regions of rising and sinking can separate chemical tracers over great depth, leaving long-lived bands of enrichment and depletion in the layers that emit the microwave signal. The microwave channels also provide information about temperature gradients in the deep weather layer. As pressure increases, the gas is compressed and warms. In a region dominated by convection, where rising and sinking motions mix heat efficiently, temperature follows a gradual increase set largely by compression. Juno's measurements are broadly consistent with such behavior, yet local variations appear because the emitting level shifts with ammonia opacity. Regions richer in ammonia can appear cooler in microwave brightness, because the radiation comes from higher levels. Regions poorer in ammonia can appear warmer because the radiometer sees deeper. Comparing shallow and deep channels helps distinguish these effects, although complete separation is not always possible. Observations indicate that the large equatorial enrichment is robust, while it remains uncertain how much of the smaller scale patchiness should be attributed to temperature contrasts rather than to ammonia contrasts. Building a global picture requires repetition. Each close pass samples a narrow swath as Jupiter rotates beneath the spacecraft. Over many orbits, different longitudes and latitudes come under the instrument, and the overlapping tracks allow broad patterns to be confirmed. Retrieval of ammonia and temperature from brightness involves radiative transfer, the accounting of how emission and absorption along a path combine into the signal that reaches the spacecraft. Uncertainties in absorption strength and mixing can shift the inferred profiles. These limits encourage cautious conclusions, favoring patterns that appear consistently across channels and across multiple passes. The microwave view also reframes the familiar contrast between belts and zones. In visible light, zones often look bright, and belts often look dark, a sign of differing cloud thickness and haze. In microwaves, the contrast can differ because the radiometer responds mainly to ammonia absorption rather than to cloud reflectivity. A region that looks bright in visible light can correspond to higher ammonia abundance and can look dimmer in microwaves because deeper warmth is hidden. A region that looks dark in visible light can correspond to ammonia depletion and can look brighter in microwaves because a deeper layer is exposed. This mismatch shows that the visible appearance is not a direct guide to deep composition. Several processes could maintain ammonia structure at depth. Large-scale circulation can transport ammonia upward in some latitudes and downward in others, renewing broad bands over time. Condensation and downward transport can also remove ammonia from upper layers and carry it deeper, leaving a depleted column above. Observations indicate depletion extending to pressures of tens of bars in some regions. It remains uncertain which combination of circulation, condensation, and downward transport dominates everywhere, because different mechanisms can produce similar microwave signatures, and because the deep atmosphere is not sampled directly. At greater depths, the concept of clouds changes with temperature and pressure. ammonia condensation becomes less important, while water and other absorbers begin to limit microwave transparency. The longest microwave wavelengths still provide a partial view into layers where pressures are dozens of bars and temperatures are well above the freezing point of water, yet the view remains indirect and filtered by absorption. Even with these limits, the radiometer offers constraints that reshape the picture of Jupiter's atmosphere. The cloud tops become the outer skin of a deeper circulation. The belts and zones become surface expressions of flows that reach downward, shaping where ammonia gathers and where it is removed. In this hidden region beneath the clouds, Juno's steady microwave measurements trace structure that persists beyond what ordinary imaging can reveal. Where Jupiter's cloud tops show long bands and small storms, some features persist for far longer than ordinary weather. These are the great vortices and storm systems, vast rotating structures that can last for years, decades, or longer. They are shaped by Jupiter's rapid rotation and by the layered nature of its atmosphere, where stable and unstable regions alternate with depth. Juno's close passes allow these storms to be examined in visible light, in infrared, and indirectly through measurements that respond to mass distribution and deep winds. A vortex is a region of circulating flow, often with a center that is calmer than the surrounding ring of faster winds. At Jupiter, vortices commonly appear as ovals. They can be anticyclones, rotating opposite to the planet's local shear in a way that tends to create a high-pressure core, or cyclones, rotating the other way. The difference matters because it influences whether air is drawn upward or pressed downward within the structure, and therefore whether clouds thicken or thin. In practice, Jupiter's vortices often show complex vertical motion, with rising in some parts and sinking in others, and with thin hazes and cloud layers responding differently at different heights. The Great Red Spot stands as the most prominent example. It is larger than Earth, and sits in the southern hemisphere between two strong jet streams that move in opposite directions. These neighbouring jets help confine it, providing a corridor where the storm can remain stable even as its outer boundary is sheared. Juno's images reveal the storm as a textured system of swirls. The outer ring contains fast winds and filamentary clouds that wrap around the vortex. Inside, cloud patterns become more irregular, with smaller eddies embedded within the larger circulation. The colour is deeper than surrounding regions, suggesting differences in cloud thickness, haze content, and perhaps the presence of colouring compounds altered by sunlight or energetic particles. Juno's infrared observations add a different view. In infrared, brightness can reflect temperature and the altitude of cloud tops. A region with higher clouds can appear cooler at certain wavelengths because it emits from a higher, colder layer. A region with clearer air can appear warmer because deeper, warmer layers are seen. The Great Red Spot often shows a complex pattern, with cooler regions where cloud tops are higher and warmer regions where the air is clearer. This indicates that the storm structure varies with height, and that the vortex influences both cloud formation and the distribution of haze. Beyond the Great Red Spot, Jupiter hosts many smaller long-lived vortices, including pale ovals and darker compact storms that travel along jet streams. In some latitudes, chains of vortices form patterns that can persist for months or years, sometimes merging into fewer larger storms. When vortices interact, their outcome depends on size, rotation sense, and the flow around them. Two similar vortices can merge into one larger structure, while a vortex encountering strong shear can be stretched and weakened until it disperses. Juno's close imaging captures these interactions as gradual changes in shape and texture rather than as abrupt events. The atmosphere's density and depth allow motion to remain fluid and continuous. with boundaries defined by gradual transitions in cloud patterns. Juno's gravity measurements contribute another layer to the understanding of storms. As the spacecraft flies close to Jupiter, tiny changes in its speed reveal variations in the planet's gravitational field. These variations arise from differences in mass distribution, including the mass associated with deep atmospheric flows. If a storm extends far downward, it involves a substantial column of moving gas, and that column can slightly change the local gravity field. By combining many passes, scientists can infer how deep the jet streams and major vortices extend. Observations indicate that Jupiter's zonal winds, the east-to-west flows that create the belts and zones, extend downward for thousands of kilometers, fading gradually rather than stopping abruptly near the clouds. This depth suggests that large-scale weather is not confined to a thin shell, but is part of a broader circulation influenced by the planet's internal heat and rotation. For the Great Red Spot specifically, the evidence suggests a substantial depth, though not one that reaches indefinitely. Observations indicate that the storm extends downward several hundred kilometers beneath the cloud tops, with its influence weakening at greater depths. This implies that while the Great Red Spot is a deep system compared with storms on Earth, it is still an atmospheric phenomenon rather than a feature rooted near the planet's center. It remains uncertain how the storm's depth changes over time as its size slowly evolves. Because the storm has been observed to shrink in visible extent in recent decades while its internal dynamics continue, the persistence of these storms raises the question of energy supply. A vortex loses energy through friction and through the mixing that occurs along its boundary. To persist, it must draw energy from its environment. On Jupiter, the strong jet streams provide a constant reservoir of kinetic energy. The shear between jets can feed vortices through instabilities that convert the energy of the background flow into rotating motion. Jupiter's internal heat also supports convection that can inject energy into the weather layer, maintaining the turbulence from which vortices can form and be sustained. In addition, the absence of a solid surface removes one source of friction common on terrestrial planets. Without mountains and land, the atmosphere can maintain large structures with fewer disruptions, though it still experiences internal friction and wave-driven mixing. Other storm types reflect different processes. There are outbreaks where a belt suddenly brightens with plumes, indicating strong upward convection over wide areas. Such events can reorganize local cloud patterns and can alter the contrast between belts and zones for months. In these outbreaks, rising columns carry gases upward, forming bright clouds and spreading hazes. Later, sinking motion can restore darker appearances as clouds thin again. Juno's microwave radiometer and visible camera together show that these events can involve deep circulation, with ammonia and other traces shifting in ways that indicate vertical transport beyond the visible layers. In this region of long-lived storms, Jupiter appears as a planet where rotation and depth combine to produce weather systems on extraordinary scales. Vortices persist because they are embedded in a powerful structured flow, and because the atmosphere is thick and continuously driven from below. Juno's close measurements show these storms as three-dimensional systems, with cloud tops that reveal only the outer expression of deeper motion, and with gravity and infrared signals adding quiet evidence of the depth and mass involved. Lightning on Jupiter is a brief signal from a deep process. It appears as a flash that lasts less than a heartbeat, yet it carries information about rising air, condensing water, and the mixing of layers beneath the visible cloud tops. Juno encounters this subject by passing swiftly over the planet, while instruments watch for light and listen for sharp radio bursts. In the darkness of Jupiter's night side, Flashes stand out more clearly, and radio waves can travel far through the thin upper air. These conditions allow Juno to detect lightning even when clouds hide the place where it forms. Lightning is produced when electrical charge separates within a storm cloud until the electric field becomes strong enough to force a conducting channel through the gas. The discharge heats that channel rapidly, creating a burst of light and a broad spray of radio emission. Juno senses the radio part with its plasma wave instrument, which registers impulsive signals with the timing expected for lightning. Juno also uses its camera to capture visible flashes, often with short exposures that freeze a point of light against the dim background of night. When radio and light are seen together, the detection becomes more secure because the same event is recorded in different ways. The presence of lightning implies a certain kind of storm physics. Charge separation is efficient when particles of different size and phase collide in a turbulent updraft. Jupiter's atmosphere is dominated by hydrogen and helium, but it still contains heavier gases that condense. Water is one of the most important because it can form both liquid and ice in the right conditions, providing mixed phase collisions that support strong charging. For this reason, lightning is widely treated as evidence that vigorous convection reaches the water cloud region. Observations indicate that many lightning events are associated with deep convective systems, rather than with the calmer cloud decks that cover much of the planet. The water cloud region is expected to lie below the ammonia cloud tops, at pressures of several bars. There the air is warmer, and water vapor can condense into droplets and ice depending on temperature. When a warm parcel rises, it cools by expansion. If it cools enough, water begins to condense and releases latent heat, the stored energy and vapor that is returned to the air during condensation. This release helps the parcel continue rising, strengthening the updraft and allowing a storm column to develop. Lightning becomes a marker that this cycle is active and intense. Juno's detections show that lightning is not evenly distributed across the planet. Many flashes cluster in belts and outbreak regions where convection is more active, and they often appear in groups that trace large storm complexes. Juno also detects lightning at high latitudes, including near the poles, revealing that vigorous convection is not confined to the equatorial bands. Nightside observations are often clearer because sunlight does not wash out faint flashes. Yet the storms themselves are driven mainly by internal heat and atmospheric instability, not by local daylight. A subtler finding emerges from the apparent altitude of some flashes. Juno observes a population sometimes described as shallow lightning, events that appear to originate higher than the deepest expected water cloud level. These flashes are fainter and seem to occur where ammonia ice clouds dominate. Their existence indicates that lightning on Jupiter may occur under more than one set of conditions. Observations indicate that ammonia and water can combine under certain temperatures and pressures to form a liquid mixture with a lowered freezing point. If such mixtures exist in rising clouds, mixed phase collisions could occur at higher altitudes than pure water would allow. It remains uncertain how common this pathway is and how much it contributes to the global lightning rate, because detection depends on viewing geometry, and because the detailed state of cloud particles in these layers is still being constrained. Lightning also provides indirect constraints on how much water is available in the deep atmosphere. If water were extremely scarce, strong mixed phase charging would be harder to sustain, and flashes would likely be rarer. If water is more abundant, deep storms can form more readily and electrical activity can be more frequent. Juno records many events over the mission, yet each pass samples only a narrow track and only a short time window, so the global flash rate must be inferred from limited coverage. Observations indicate that lightning is common enough to support a substantial water inventory. while it remains uncertain how that inventory varies with depth and latitude, because storm occurrence itself depends on circulation and stability. Deep convection on Jupiter has a distinctive style shaped by a thick atmosphere and by rapid rotation. Storms draw on condensable gases mixed into the air rather than on surface reservoirs, where water vapor is abundant and the atmosphere is unstable. Rising columns can carry material upward across many pressure levels. The tops of these columns spread into bright cloud shields, while surrounding air subsides and clears. Jet streams steer these systems, stretching their edges into filaments and organizing them into belts and zones. Lightning occurs when turbulence within the rising and falling regions produces strong charge separation. Electrical activity also interacts with microphysics, the behavior of particles within clouds. Droplets and ice can grow, collide, and fall, carrying material downward. In the water cloud region, precipitation can remove water and dissolved substances from higher layers. A proposed process involves ammonia being carried downward within falling hail, like particles that form when ammonia and water combine, allowing ammonia to be transported to deeper layers even when convection remains active above. Observations indicate microwave signatures consistent with strong vertical transport and with localized depletion or enrichment of ammonia near active storms. It remains uncertain how frequently this precipitation process occurs and how it varies with latitude, because it depends on temperature structure, mixing, and the availability of both water and ammonia. In this region of Jupiter's atmosphere, lightning becomes more than a spectacle. It traces vertical energy flow, marking where rising motion reaches depths where water participates, where charge can separate, and where storms grow tall enough to generate flashes detectable from orbit. Juno's ability to hear radio bursts and see faint optical flashes provides a way to map deep convection across the planet. The result is a view of Jupiter's hidden weather as active and uneven, with convective towers that sometimes reach upward toward the cloud tops while remaining rooted in the warmer, denser layers beneath. Across Jupiter's cloud tops, the fastest motions are organized into long rivers of wind. These are the jet streams, bands of flow that circle the planet in alternating directions. They are called zonal winds because they follow lines of latitude, forming belts of speed that can persist for years. In the visible clouds, the jets reveal themselves through sharp boundaries where textures change, where storms are stretched into ovals, and where filaments are drawn into thin threads. In the deeper weather layer, the same jets shape the distribution of gases and the pattern of rising and sinking that feeds the clouds. A jet forms where the balance of forces favors long, steady flow rather than rapid mixing. Jupiter rotates rapidly, and that rotation makes moving air feel an apparent deflection called the Coriolis effect. In the northern hemisphere, motion tends to bend to the right, and in the southern hemisphere it tends to bend to the left. When this deflection is strong compared with friction, winds align in bands that run around the planet. The result is a staircase of alternating jets, each separated by regions of shear where neighboring bands slide past one another. These shear zones generate eddies, and the eddies can return energy to the jets, helping them endure. Juno studies these winds in two complementary ways. One approach uses images of cloud features. By tracking the motion of small storms and bright plumes, the speed of the wind at the cloud tops can be estimated. Yet cloud tracking cannot reveal how far downward the winds extend, because clouds are only the upper expression of a deeper flow. The second approach uses gravity. As Juno passes close to Jupiter, radio signals exchanged with Earth record tiny changes in the spacecraft's speed. These changes occur because Jupiter's gravity field is not perfectly smooth. The planet is ablate from rapid rotation, and its interior has layers with different densities. Deep winds also move mass around, creating small additional variations. If winds are confined to a thin shell near the clouds, their mass effect is small. If winds extend deeper, the moving mass is larger and the signature becomes stronger. By analysing many close passes, scientists infer how much of the gravity field is consistent with deep, zonal flow. The method relies on the fact that winds are not distributed evenly with latitude, so they shift mass in a patterned way. Those shifts leave a fingerprint in the small departures of gravity from an ideal, perfectly layered planet. In the analysis, the smooth contribution from Jupiter's overall shape and interior layering is separated from the subtler contribution expected from moving atmospheric columns. Observations indicate that the wind-related signature is strongest for the largest jets, where the flow covers wide latitudes and persists over time, while it remains uncertain how much short-lived turbulence contributes because transient structures average away more readily in repeated passes. Observations indicate that Jupiter's jet streams extend downward for thousands of kilometers beneath the visible clouds. The inferred depth is on the order of about 3,000 kilometers, with the winds gradually weakening with depth rather than stopping abruptly. This means the jets are not mere surface currents. They occupy a substantial fraction of the outer envelope, carrying momentum through layers where pressure rises from the cloud tops to many hundreds of bars. It remains uncertain how the detailed vertical structure varies from one latitude to another, because gravity measurements constrain the overall depth and strength, but cannot map every fine variation with the clarity of images. A deep jet must be maintained against forces that would otherwise erase it. Turbulence mixes momentum across latitudes, smoothing differences in speed. At the same time, Jupiter's rotation encourages long-lived bands, and the planet's internal heat drives convection that continually supplies motion. In this picture, eddies generated by convection and shear can merge into larger structures and transfer energy into the jets, building organized flow out of disorder. The cloud tops show this as constant formation and decay of vortices that drift along the jets, with some being absorbed and others surviving for long periods. As the jets extend downward, the properties of the gas change. Pressure increases and the atmosphere becomes denser. Temperature rises, and the ability of gases to condense into clouds diminishes for some constituents. At still greater depths, hydrogen becomes a better electrical conductor. This gradual increase in conductivity matters because moving, conducting fluid in a magnetic field generates electrical currents, and those currents experience forces that can oppose the motion. In Jupiter, the internal magnetic field threads the deep layers, and the interaction between flow and field provides a natural way to break differential rotation, the tendency for different latitudes to move at different speeds. Observations indicate that the jets weaken below a few thousand kilometers, consistent with the idea that magnetic forces become increasingly important as conductivity rises. It remains uncertain how sharply this transition occurs, because conductivity increases gradually, and because the magnetic field varies with location. The microwave radiometer adds an atmospheric tracer to this dynamical picture. Patterns of ammonia abundance and brightness at microwave wavelengths persist beneath the cloud tops and align broadly with the banded circulation. Where jets and circulation create sustained rising or sinking, ammonia can be carried upward or downward over great depth, leaving bands of enrichment and depletion. These tracer patterns indicate that the winds are tied to vertical motion, not only to horizontal speed. A jet can act as a barrier that limits mixing across latitude, allowing neighbouring bands to maintain different compositions for long times, even while storms and eddies slowly blur the contrasts. In the jet streams, Jupiter's atmosphere becomes a rotating engine of organised motion. The clouds reveal the speed at the top, the microwaves reveal tracer bands below, and the gravity field reveals how far the motion reaches into the planet's outer envelope. This layered view shows that the winds are deep enough to carry substantial mass, yet shallow enough to remain part of the outer weather layer, where convection, rotation, and the growing influence of magnetic breaking together shape the steady, banded flow. Below the levels where clouds form and fade, Jupiter's atmosphere becomes a deeper envelope of gas in which the idea of weather slowly loses meaning. The familiar belts and zones remain visible because cloud particles reflect sunlight, yet the winds that shape those patterns extend downward into warmer layers where sunlight no longer reaches. As pressure increases, the air grows denser and more uniform in appearance, and the main ingredients, hydrogen and helium, dominate almost completely. In this region, hydrogen remains in molecular form, meaning that each molecule contains two hydrogen atoms bound together, and helium remains as single atoms mix through the gas. The mixture behaves like a fluid that can flow, compress, and convect, and its properties change smoothly with depth rather than in sharp steps. Pressure is the first change that defines this inward region. At the cloud tops, pressure is near 1 bar, similar to the surface pressure on Earth. Deeper down, the weight of overlying gas increases the pressure rapidly. At tens of bars, clouds related to ammonia and water become less relevant to what can be seen, yet the gas is still far from any solid boundary. At hundreds of bars, the density becomes high enough that the gas begins to feel less like a thin atmosphere and more like a planetary interior. The increase continues to thousands of bars, with each deeper layer compressed by the immense weight above it. Even so, this is still a continuous envelope, not a sequence of shells separated by empty gaps. With compression comes warming. As gas is squeezed, it heats, and in a convecting planet this warming largely follows a smooth curve set by the balance between rising and sinking. Convection remains important because Jupiter releases internal heat that leaks outward over long time scales. Warm gas from deeper levels rises, expands, and cools, while cooler gas from above sinks, compresses, and warms. This overturning mixes heat efficiently and tends to keep the temperature profile close to an adiabatic state, meaning a state where parcels of gas change temperature mainly by expansion and compression rather than by gaining or losing heat to their surroundings. The result is a deep interior where temperature rises steadily with pressure in a way that is predictable in broad outline, even though local variations can occur in the outer weather layer. In the molecular hydrogen region, the gas remains a weak electrical conductor compared with layers at greater depth, so magnetic forces play a limited role in shaping the bulk flow described here. The motion is governed mainly by fluid dynamics and by rotation, with the Coriolis effect still organizing large-scale circulation into broad bands. Yet as depth increases, the density grows, and motions that are dramatic near the cloud tops become more subtle when expressed as visible features. The same mass of moving gas carries more momentum, and changes in speed occur over larger length scales. Storm systems that are distinct at the surface blend into a background of slow, large-scale circulation. Composition also becomes simpler. Above, small fractions of methane, ammonia, water, and other compounds shape clouds and colours. Deeper down, these heavier molecules remain present but are increasingly diluted by the overwhelming abundance of hydrogen and helium. Some constituents can be carried upward and downward by convection, and their distribution can be shaped by circulation, as Juno's microwave measurements suggest for ammonia in the outer layers. In the deeper molecular hydrogen envelope, most of the mass is still hydrogen and helium, and the main questions become how well mixed the helium is and how efficiently heat is transported. Observations indicate that Jupiter's outer envelope is mostly convective and well mixed in hydrogen and helium over large regions, while it remains uncertain whether there are stable layers where mixing is reduced, because such layers would be difficult to detect from orbit and would depend on subtle differences in composition and heat flow. The idea of a boundary between atmosphere and interior becomes less useful in this region. There is no place where gas suddenly becomes something else. Instead, pressure and temperature change the gas continuously. The density increases from values typical of an atmosphere to values more comparable to fluids under high pressure. The speed of sound rises with temperature and with the stiffness of the compressed gas, and the ability of pressure waves to travel changes accordingly. In a convecting interior, these waves can carry information about bulk structure, yet they are not directly measured in the same way as on a rocky planet. The internal structure must be inferred from gravity and from models of how hydrogen and helium behave under extreme conditions. Juno's role in this region is largely indirect. The spacecraft does not descend into the atmosphere, but its gravity measurements constrain how mass is distributed within Jupiter. The planet's rapid rotation makes it bulge at the equator, and that shape affects the gravity field. Deep winds also shift mass in latitude, leaving additional signatures. By combining these measurements with laboratory and theoretical understanding of hydrogen and helium under pressure, scientists infer the range of density profiles that fit both the gravity data and the known mass and radius of Jupiter. In the molecular envelope, these inferences indicate a smooth increase of density with depth, consistent with a fluid planet lacking any solid surface in the outer layers. In this same region, pressure changes how closely hydrogen molecules pack together, altering compressibility and the way the gas stores heat. A useful term is equation of state, meaning the relationship among pressure, temperature, and density for a given material. For Jupiter, this relationship is tested in laboratories and in calculations, then applied to the gravity constraints to narrow the plausible range of interior conditions. Within this compressed gas, time acts differently than at the cloud tops. Motions can remain vigorous, yet changes in visible appearance are slow because the layers are hidden. Heat transport is continuous, carrying energy outward through rising and sinking. The balance between upward transport of heat and the organizing effect of rotation supports a broad pattern of circulation that extends far beneath the clouds. In this region, Jupiter is best understood as a warm, rotating ocean of molecular hydrogen and helium, layered only by pressure and held together by gravity rather than by any solid framework. Deeper inside Jupiter's outer envelope, pressure and temperature rise, and the gas becomes more able to carry electrical currents. In these layers, motion is no longer only fluid flow shaped by rotation. Conducting material moving through a magnetic field can generate new magnetic fields, and this process can sustain a planet-wide magnetic presence over long timescales. The sustained generation of a magnetic field by moving conducting fluid is called a dynamo. Jupiter's magnetic field is strong and extensive, and it shapes the space environment far beyond the clouds. Juno's close polar orbits provide an unusually clear way to measure that field and to infer where, within Jupiter, the dynamo action is most active. A magnetic field is a pattern of direction and strength in space. Near the planet, the field is dominated by a large-scale component that resembles a bar magnet. with field lines emerging from one hemisphere and returning in the other. Yet Jupiter's field is not a perfect dipole. It contains stronger and weaker regions, patches where the field intensifies, and structures that indicate currents within the planet. Mapping these details requires repeated measurements at many locations, combined into a global model. Juno carries a high-precision magnetometer mounted on a long boom, designed to reduce interference from the spacecraft. On each close pass, the instrument samples the field continuously as the spacecraft sweeps from one pole to the other. Because Juno flies very close to Jupiter at Periovi, the point of closest approach, the measured field includes fine details that would be blurred at larger distances. The signal rises steeply as the spacecraft approaches, and the shape of that rise depends on how the field varies with latitude and longitude. When many close passes are combined, the field can be expressed as components of different spatial scales, from the broad dipole to smaller patterns that vary more quickly across the planet. The smaller patterns are especially valuable because they carry information about currents and flow closer to the dynamo region. Juno's measurements show that Jupiter's field is unusually uneven in certain regions. In some longitudes, the field strengthens sharply over relatively short distances, producing localized intensity that stands out against the surrounding pattern. This indicates that the dynamo does not produce a smooth field. Instead, it produces concentrated features, as if internal flow generates strong magnetic patches in some areas more than others. The overall field is also slightly offset from the planet's center, meaning that the best fit dipole is displaced relative to Jupiter's geometric center. Such an offset can arise when the dynamo region is not symmetric, or when flows within it produce uneven magnetic contributions. The orientation of the field adds another constraint. Jupiter's magnetic axis is only modestly tilted relative to its rotation axis. The small tilt means that as Jupiter rotates, the main field remains nearly aligned with the spin, supporting a stable large-scale magnetosphere. At the same time, the more complex parts of the field vary with longitude and create differences between regions that would otherwise be similar. These differences appear in how field strength and direction change along Juno's path, and in how the field maps to the polar atmosphere. The result is a field that is steady in broad orientation, yet richly structured in local detail. A dynamo depends on the properties of the conducting layer and on the flow within it. The conducting layer must be deep enough and dense enough to allow electrical currents to persist, rather than dissipate immediately. It must also be in motion, because static conductors cannot sustain a magnetic field against decay. The motion is driven by convection, the slow rise of warmer material and the sinking of cooler material, powered by Jupiter's internal heat. Rotation shapes this convection into organized patterns that favor long, coherent currents. Juno's field maps are therefore indirect portraits of deep circulation, translated into magnetism that reaches the spacecraft. The way the field varies with distance provides clues about the depth of its sources. Field components that change rapidly with position tend to be produced by currents closer to the outer envelope, while smoother components can originate deeper. By measuring both broad and fine structure, Juno helps constrain how thick the active dynamo region may be and how close to the weather layer it extends. Observations indicate that some magnetic features are strong and localized enough to suggest contributions from relatively shallow depths compared with older, simpler models. It remains uncertain whether this requires a distinct shallow dynamo layer or whether a single dynamo region with uneven flow can produce the same outcome. Time adds another dimension. If the dynamo flow changes, the magnetic field can evolve, producing slow shifts called secular variation. Detecting this at Jupiter requires repeated high-precision measurements over years. Juno's extended mission provides such coverage, and comparisons among passes reveal small but meaningful changes in the field model. Observations indicate that some features shift and evolve over time, consistent with an active dynamo rather than a fixed magnetic imprint. It remains uncertain how to separate true internal change from the effects of external currents in the magnetosphere, because Jupiter's space environment also carries currents that can slightly perturb the field measured near the planet. The magnetic map connects to the upper atmosphere through auroras. Charged particles travel along magnetic field lines, so the detailed shape of those lines influences where particles precipitate and where emissions brighten. When the field has localized strong regions, the mapping between magnetosphere and atmosphere becomes uneven, and neighboring areas can connect to different regions of space. Juno's combined measurements of magnetism and polar emissions allow these connections to be traced with fewer assumptions than remote viewing alone. In this inward region, Jupiter appears as an engine where rotation, convection, and electrical conductivity combine to produce a magnetic field of great strength and intricate form. Juno's magnetometer turns that field into a detailed map, showing that Jupiter's magnetism is not a simple, smooth dipole, but a structured outcome of deep fluid motion. The measurements provide firm evidence for dynamo action in the conducting layers beneath the weather and constrain how uneven and how active that dynamo must be, while leaving open important uncertainties about the exact depth and layering of the region that sustains it. Deeper beneath Jupiter's cloud layers and the region where molecular hydrogen dominates, pressure reaches levels where hydrogen begins to change its character. Hydrogen is still the same element, yet under immense compression its electrons become less tightly bound to individual molecules. The fluid starts to conduct electricity far more easily, because its internal structure allows electrical charges to move through it. This state is often called metallic hydrogen, meaning hydrogen that behaves in some ways like a metal by carrying electrical current. It is not a solid sheet. It is a dense, hot fluid that can flow, convect, and respond to Jupiter's rotation, while also participating in the dynamo that generates the magnetic field. In this region, the transition is gradual rather than abrupt. Molecular hydrogen, where atoms are paired into molecules, gives way with increasing depth to a fluid where the molecules are partly broken and the electrons are freer to move. The change depends on pressure and temperature and may occur over a broad range rather than at a single clear boundary. Observations indicate that the conductivity of the interior rises steadily inward, supporting the idea that the magnetic field is generated in a thick shell. It remains uncertain how sharp the transition is in Jupiter, because the needed conditions are difficult to reproduce precisely, and because interior temperatures cannot be measured directly. Alongside hydrogen, helium remains the second most abundant ingredient. Helium does not readily form molecules in these conditions, and it tends to remain chemically inert. Yet the physical relationship between helium and hydrogen changes as hydrogen becomes metallic. In the outer molecular envelope, helium is mostly mixed with hydrogen as a well-blended fluid. Deeper in, theory and experiments suggest that helium may become less soluble in metallic hydrogen under certain combinations of pressure and temperature. When a substance becomes less soluble, it separates from the mixture, forming a distinct phase, like droplets forming in a liquid that can no longer hold a dissolved component. In Jupiter, this possible separation is often described as helium rain, a shorthand for the idea that helium could form droplets and sink inward through the metallic hydrogen region. If helium separates, it influences Jupiter in several connected ways. It changes composition with depth, with the outer envelope becoming slightly depleted in helium while deeper layers become enriched. It can release energy, because sinking droplets convert gravitational energy into heat, adding an internal power source beyond slow cooling. It can also change how heat is transported. A layer with composition gradients can resist mixing, because lighter, helium-poor fluid above and heavier, helium-rich fluid below create a stable stratification that discourages vigorous convection. The result can be a region where heat moves more slowly and where temperature differences can be maintained. Juno's measurements cannot see helium droplets directly, yet they constrain the possibility through gravity and through the overall structure required to match Jupiter's mass and size. Models that fit the gravity field must also fit a realistic distribution of density. Helium enrichment raises density, while helium depletion lowers it. If helium separation occurs, the density profile changes in a way that can shift the gravity harmonics inferred from spacecraft tracking. Observations indicate that Jupiter's interior cannot be described as a simple, perfectly mixed hydrogen and helium fluid from top to bottom. It remains uncertain how much of that complexity is due to helium separation, compared with other processes such as mixing of heavier elements. Helium separation can also leave a signature in the upper atmosphere. The helium abundance in the outer envelope can be estimated from remote sensing and from earlier in situ sampling, offering a boundary condition for interior models. If the observed helium abundance is lower than the primordial mixture expected from the early solar system, it supports the idea that helium has migrated inward. Observations indicate that Jupiter's atmosphere contains slightly less helium than a primordial mixture, consistent with some degree of separation. It remains uncertain exactly where within the planet the separation becomes significant and how the process changes over time, because the separation depends sensitively on the temperature profile at depth. Within the metallic hydrogen region, electrical conductivity becomes high enough that flow interacts strongly with magnetic fields. Conducting fluid moving through the existing magnetic field generates currents, and those currents experience forces that can shape the flow. This feedback can damp some kinds of differential motion while favoring others, and it can influence how heat and composition are transported. A stable compositional gradient associated with helium separation could confine vigorous convection to certain depths, altering where the strongest magnetic field is generated and how it is structured. Heat transport in this region is central to Jupiter's long-term evolution. The planet slowly radiates energy to space, and to do so it must carry heat from deep layers outward. In a fully convective interior, this transport is efficient and the temperature profile stays smooth. If helium separation introduces a stabilizing gradient, transport could slow in that zone, changing the temperatures above and below it. Over billions of years, this can influence the planet's cooling rate. Observations indicate that Jupiter still emits more energy than it receives from sunlight, confirming ongoing internal heat flow. It remains uncertain how much of that heat is supplied by separation processes versus residual heat from formation, because both can contribute. The concept of helium rain is not a weather system in the ordinary sense. It is a phase separation within a hot, dense fluid, occurring far below visible layers. If it occurs, helium forms a denser phase that sinks through a surrounding hydrogen-rich fluid. As the helium moves inward, the outer envelope is left slightly lighter in helium and the deeper region slightly heavier. The process is slow, steady, and governed by dense matter physics rather than by cloud microphysics. In this layer, Jupiter is best imagined as a deep, slowly moving ocean of dense fluid, where hydrogen becomes an electrical conductor and where helium may no longer remain evenly mixed. The physics is governed by compression, by the motion of electrons in dense matter, and by the gentle but relentless pull of gravity. Juno's magnetic field maps point to a dynamo operating within conducting layers, and the gravity field points to an interior that is compositionally complex. Together they support an inward picture in which metallic hydrogen and helium separation play a significant role, while leaving room for uncertainty about the exact depth and strength of these processes. At the centre of Jupiter, the inward path arrives at a place that is not a surface and not a single boundary. Gravity holds the deepest material in a state where pressure and temperature are extreme, and where ordinary distinctions between layers become blurred. The word core is often used for the region where heavy elements, meaning elements heavier than hydrogen and helium, are most concentrated. Yet Juno's gravity measurements suggest that Jupiter's core is not necessarily a compact, sharply edged object. Instead, the planet may contain a diluted core, a broad inner region where heavy elements are mixed outward into the surrounding hydrogen and helium over a substantial fraction of the radius. The evidence comes from how Jupiter's mass is distributed. Juno measures the planet's gravitational field by tracking subtle changes in the spacecraft's motion during close passes. Those changes reveal the gravity harmonics, the patterns that describe how a mass is arranged within a rapidly rotating, slightly flattened planet. A planet with a small, dense core and a well-mixed envelope produces one set of harmonics. A planet with heavy elements spread through a wider region produces another. When models attempt to match the gravity data while also matching Jupiter's overall mass, radius, and rotation, the results favour an interior where heavy material is not confined to a tight ball at the centre. Observations indicate a central enrichment that extends outward, with the transition from heavy-rich to lighter material occurring gradually rather than abruptly. It remains uncertain exactly how far this enriched region extends, because different interior models can fit the data within uncertainties while using different assumptions about the behaviour of hydrogen and helium under pressure. The phrase diluted core captures a physical picture. In the deepest interior, heavy elements may be mixed with hydrogen and helium in a high-pressure fluid, producing a region that is denser than the outer envelope but not separated by a clear boundary. Instead of a rocky or icy sphere embedded inside gas, there may be a gradient, with the highest concentration of heavy elements at the centre and a declining concentration moving outward. This does not mean the centre is light or empty. It means the change in composition is spread over a wide zone, like salt gradually thinning in a stirred solution, rather than sitting as a solid pile at the bottom. Several processes could produce this structure. In the early solar system, Jupiter likely begins with the accumulation of solids, including rock and ice, that build a dense centre before gas accretion becomes dominant. As the planet grows, gas floods in, and the interior heats under compression. Under those conditions, some materials that would be solid near Earth can dissolve into the surrounding hydrogen and helium, forming mixtures rather than remaining as a separate phase. Over time, convection and mixing can transport dissolved heavy material outward, especially if the temperature is high enough to keep the mixture fluid. Observations indicate that mixing of heavy elements is plausible in such conditions, while it remains uncertain how efficient the mixing is and whether stable compositional layering slows it. Another pathway involves impacts during formation. In a crowded young solar system, large bodies can collide with a growing giant planet. A sufficiently large impact can deposit heavy material deep into the interior and can stir existing layers. Such stirring could blur a previously sharp core boundary by mixing heavy elements into higher regions. Yet even without a single dramatic event, gradual accretion of solids and ongoing interior motion can produce partial mixing. The present gravity field constrains the outcome, not the exact history. It points to a state where heavy elements are distributed across a significant inner fraction, consistent with either early mixing, later mixing, or a combination. The interior structure is also influenced by how heat moves. If the deep interior convects freely, it mixes both heat and composition, tending to smooth gradients. If there are layers where composition changes with depth, those gradients can resist mixing. A stabilizing gradient forms when denser, heavy rich fluid lies beneath lighter, heavy poor fluid. In that case, convection is reduced, and heat may move more slowly by conduction or by limited layered convection. This can preserve a diluted gradient over long timescales. Observations indicate that Jupiter's interior is not fully uniform, consistent with some degree of stable layering. It remains uncertain how thick these stable regions are and how they interact with the flows that generate the magnetic field. Because magnetic constraints and gravity constraints must be reconciled with dense matter physics that is still being refined. Heavy elements in Jupiter are thought to include rock-forming materials, water-related compounds, and other volatiles captured during formation. Under extreme pressures, these materials do not behave as ordinary solids or liquids. They can form dense fluids and complex mixtures with hydrogen. Laboratory experiments and theoretical calculations explore how such substances dissolve and mix at high pressures and high temperatures. Yet the exact behavior at Jupiter's deepest conditions is challenging to pin down. This is one reason interior models retain ranges rather than single definitive answers. Observations indicate that Jupiter contains more heavy elements than the Sun does in relative proportion, consistent with formation by accretion of solids followed by gas capture. It remains uncertain how these heavy elements are partitioned today between a central enrichment, the surrounding metallic hydrogen region, and the outer molecular envelope. The diluted core concept also links to the planet's overall density. Jupiter's average density is low compared with rocky planets because it is mostly hydrogen and helium. Yet a modest fraction of heavy material can still have a strong effect on the deep density profile. If heavy elements are confined tightly at the center, the density rises sharply inward. If they are spread out, the density rises more gradually. The gravity harmonics measured by Juno are sensitive to this difference, especially when combined with a planet's rapid rotation, which couples interior density structure to the shape of equipotential surfaces. Matching the data often favors a smoother increase, implying a core region that is extended and mixed. At the very center, pressure is immense and temperature is high enough that all material is in a dense, hot state. There is no solid ground. The deepest region is a fluid mixture under extreme compression, with heavy elements concentrated most strongly at the center and hydrogen and helium still present. Motion there is slow compared with the visible storms above, yet it is not static. Over long time scales, heat leaks outward and buoyancy drives gentle circulation where mixing is permitted. Where mixing is limited, gradients remain and the interior becomes stratified, meaning layered by density and composition. Juno's findings therefore reshape the inward image of Jupiter. The planet is not a simple gas shell wrapped around a small hard core. It is a continuous fluid world in which composition changes gradually with depth. At the center, heavy material is present in large amount, yet it may be distributed across a broad inner region, rather than contained in a compact sphere. Observations indicate that this diluted core is consistent with the measured gravity field and with plausible behavior of dense mixtures. While it remains uncertain exactly how the heavy elements are arranged in detail and how the arrangement evolves over time, the journey inward settles into a quiet picture of Jupiter as a layered, moving world without solid ground. Above, sunlight touches hazes and cloud tops, and beneath, heat rises from the planet's interior through gas compressed into dense fluid. The same planet that shows bright bands in reflected light also holds deeper bands of motion revealed by gravity and by microwaves that slip through the upper clouds. Wind, chemistry, and condensation shape the outer layers, while pressure and conductivity reshape hydrogen into a medium that can carry currents and sustain a magnetic field. In the polar regions, energy from space meets the upper air and becomes auroral light and warmth, linking the distant magnetosphere to the thin conducting layers above the clouds. Farther down, weather becomes less visible, but not less real. Jets reach downward, storms draw power from internal heat, and lightning briefly marks where deep convection rises through heavier layers. Still deeper, the planet becomes an ocean of hydrogen and helium, warming under compression, slowly turning into a better conductor as electrons move more freely. Helium may separate and drift inward, altering composition and releasing heat in a steady, hidden way. At the center, gravity gathers the heaviest material into a broad enrichment rather than a sharp core, suggesting a history of mixing and dissolution under extreme conditions. The planet's structure becomes a continuous gradient, from space shaped by magnetic lines to an interior shaped by pressure and long-lived flow. Jupiter remains a giant in constant motion, yet its changes unfold on quiet timescales, driven by slow cooling and by the steady turning of a massive world.